we can see that this spline function is much better than the previous one. And if you do a comparison to them directly, you may find that this one is obtained by B splines, and the other one is by cubic splines. So normally, we better use B splines for better interpolation results. However, if you want to find the theoretical form or mathematical form, you better use the cubic splines, because they are given as cubic functions like this. But for the interpolation result, you better use B splines. Well, these are one-dimensional interpolation. And the spline objects are also usable for multi-dimensional interpolation problems. For instance, if you are using a cubic spline, you can use a CS API to find one-dimensional spline approximation. If you have two-dimensional interpolation problems, or even high-dimensional problems, you can use a function call like this. And then you can use FNPLT to show the results. So this function and the other function for B-splines can be used for multi-dimensional or high-dimensional problems. So let's consider this example again, which is a two-dimensional problem. We can generate a set of data, which is not necessarily to be as gray data. We can generate any kind of data. We can generate data using commands like this. Sorry, this is the sorry, I think I'm wrong. The CS API object can only be used for quick data. It cannot be used for any distributed data. So we can use command like this to generate the sample data sets. And then we can use CS API to create an object. And then we can use FNPLT to draw surface plot. The surface plot can be drawn automatically. You do not have to specify the form of the display result. For three-dimensional problems, it will draw surface plot automatically. This is the interpolation result, but the interpolation points are selected automatically. You do not have to specify the space between points. So this one are obtained by interpolation method, by spline interpolation method. And if you are using a B-spline, you will have better results normally. And there is another function I want to talk about, which is function FNVAL. A function like this is equivalent to the function inter P1 x, y, x1 spline I used earlier. And this part is indicated in the object S already, because S is created on top of X and Y. And this one is the interpolation point, but the spline function is used for cubic spline approximation. So this one can also be used to perform interpolation and get interpolation data. So which is quite similar to the function like this. And it also works for high-dimensional function approximations. And based on the spline function, we will talk about numerical differentiation or numerical integration from data rather than from formulas. And the problem could be stated something like this. Once you have certain points, sample points you measure from experiments, you can for sure get a curve. So the question is, what is the first order derivative from this point? And since the function fx is not given, so you must solve the problem using numerical method rather than direct method. If you know the function, of course, you can use the f function to find the derivatives. However, if the function is not given, you better use numerical method to find the first order, second order, or even high order derivatives from the sample data. So this is what I call here numerical differentiation problems. Also, you can solve numerical integration problems. And this kind of problem is slightly different from the term numerical quadrature. I use a slightly different term. Actually, in chapter 3 of the book, I used numerical quadrature. However, here I try to use the term numerical differentiation. In your numerical analysis courses, what you are solving is numerical quadrature problems, which is stated like this: A and B definite integral in a certain interval A and B, where A and B are given, you can find the value for it. However, for numerical integration problems and what you can solve from spline functions, you can expect some results like this, where P is a function. You can find the integration at all these functions rather than for the area with the quadrature method. So they are different. For this method, you can only find the area in this interval. However, with the numerical integration, you can find all the integration method from all these points rather than the definite integral for the whole interval. So they are slightly different. So how can I solve this kind of problems? Since you have already created an object F, which can either be a cubic object or a spline object, you can easily find the case order derivative with the use of the function f(n)(der). You can easily find the function. And for multivariable problems, you can easily find the partial derivatives using the same function. But for the object, you can find the partial derivative. For the first independent variable, you can have k1 order derivative. For the second variable, you can have k2 order derivative. So you can easily find the high order derivative or partial derivative of the function. So this can be obtained using numerical method. So this is a numerical differentiation. You can either find